we're going to transition to Chandralekha. And Chandralekha, one of the lead authors of the curriculum that is at your table. So there are 5 different curriculum documents you can choose from at your tables. We have chemistry, physics, mathematics, computer science, and middle school STEM. So we tried to put a few copies of each on all of the tables so that you can refer to them as Chandralekha is speaking about their development and their alignment with NGSS. All right, so with that, I'll hand it over to you, Chandralekha.
Okay, thank you so much, Angela. I really appreciate, how you have actually organized this awesome conference, and you've been doing such a great job with the professional development, because Quantum Education Leadership Conference is really important, especially to celebrate this International Year of Quantum Science and Technology. And as Emily Edwards just said, she and I work very closely, and we are one team, and we have been working on a lot of things. And I'm particularly going to focus on the quantum information science framework for K-12 education in the US. So as everybody's been talking about, 100 years ago, we had the first quantum revolution that basically not only just helped us formulate the theory of quantum physics, but also gave us things like transistors, semiconductor devices, microprocessors, lasers, nuclear energy, a lot of things that we take for granted now. All the electronic devices that you have been made possible by this. But now is a really exciting time in this century because of the way that we are able to manipulate and, process quantum information. So that means that, in this century, we are able to actually coherently control quantum systems, and that gives us opportunities to think about applications in quantum information science and technology, including making quantum computers or quantum sensing devices or quantum communication devices, like you just heard about quantum internet and things like that. So it's a very exciting time for all the people who do science, because it could be that, once we have a quantum computer that is scalable, maybe in several decades in the future, but if we do, then we are going to be able to do lots of cool research, and we are going to have applications in things that we haven't even thought about. Because, you've already heard about applications of quantum in, for example, how your credit card encryption schemes could be compromised because of the fact that, products of prime number factoring is a really hard thing. But that could actually become an easy thing if we have quantum computers. But also, quantum computing could actually help us, can actually help us, for example, in agricultural security, and it can help us with like drug design and many, many other applications. So it's a very exciting time. And we really need to think about careers in quantum information science and technology for scientists and engineers, as Emily just emphasized. So you can see here, lots of different kinds of people come together, because quantum information science and technology is not just physics. And moreover, it's not just that we are needing people who are quantum proficient, like, for example, people who have a deep understanding of quantum physics, for example, but we also are looking for people who are going to play a role as quantum adjacent people or quantum aware people in the quantum industries. For example, cryogenic engineer, somebody who's cooling things down, or somebody who's vacuum technology expert, or quantum software person, or program manager, business developer, policymaker, teachers and educational professionals. We need a lot of mathematicians, nanofabrication process. And the point is that all of these different people will come together, but this means that we really need to get students excited about this field now. Because if we start early, students can develop intuition, and they will want to take courses later that will actually help them solidify those intuitive ideas. And also they'll find out about all these careers, whether they're actually adjacent careers or proficient careers. And the great thing is that, once you know about the fact that there is superposition and entanglement and things like that, it wouldn't be that spooky and unfamiliar. Because, it's like learning 2 languages. I know, my mother tongue is Hindi, And if I know Hindi and English, both of these things I learned from when I was really a little kid, it doesn't take me that much time to switch between those two things depending upon who needs what. So if we really learned quantum early, that would not be spooky, and you would be able to switch back and forth between what quantum superposition and entanglement means as opposed to, what classical world does. So in that sense, also, early exposure will get us to diverse pools of students because, the diversity in college level science courses is already pretty bad, as you all know. So basically in 2020, as Emily just said to you, the Office of Science and Technology Policy and National Science Foundation put together a working group that included academics, industry people, national lab people, and they were tasked with this job of developing key concepts for quantum information science for K through 12. And notice that this is what we are using as the seed for developing these frameworks with the help of K through 12 teachers. So the concepts that we came up with as key concepts were these concepts that you can see here, like quantum states, quantum bit or qubit, which is a generalization of classical bit. So this thing can be in a superposition of 0 and 1, not just 0 or 1. Quantum measurement, you already heard a lot about it, that there's something really weird about quantum mechanics, that it actually changes the quantum state, something that you don't see in classical systems. Entanglement, again, is a very interesting kind of correlation that is very different from classical correlations. Quantum coherence, again, that is a very interesting phenomenon, and this is the reason why quantum computing, quantum communication, and quantum sensing is going to actually take a long, long time to actually make scalable, because of the fact that decoherence in quantum systems is a big problem. Systems decohere much more easily, and it's really hard to correct errors and make fault-tolerant quantum computers, for example. But we are really excited about all these applications in computing, communication, like quantum internet, and making next generation of sensors. You're already familiar with MRI machines, but we will have next generation of sensors that will really be exciting. They can take advantage of quantum entanglement and things like that. So this was the report that came out for key concepts in quantum information science. And we used that to actually develop this framework, as Emily talked about it before me. And so our goal is to make these frameworks be useful for developing curricula and pedagogies and for strengthening connections with national and state standards. So each framework, and as Emily said, we have a separate framework for computer science, physics, chemistry, mathematics, and one for middle school, because there is no need to have a unified framework. And it's really important to keep in mind what are the disciplinary affordances and constraints in each of these disciplines and at the level that we are talking about. And so we really worked with the teacher to make sure that these frameworks are based on the norms and curricular focus of each of the disciplines and grade level. And we also made sure that the concepts are emphasized as appropriate for those kinds of things. So for example, in computer science, there was no need to emphasize quantum sensing because that was not a relevant thing for those people, but quantum computing was relevant. And physics and chemistry framework, as you can imagine, are much closer to each other than the computer science and math framework to physics and chemistry. And so we had 5 different sets of K through 12 teacher groups and educational professionals working together. And it was supported by us, like Emily, me, and Diana, and other people. And we had many, many Zoom meetings in the evenings and weekends over a 2-year period to come up with these standards. And so, as I said, we centered the classroom experiences of the teachers. So they played a central role in coming up with these frameworks. Their voices were very important. And notice that these frameworks explicitly focus on the next generation science standards disciplinary core ideas, as well as science and engineering practices. So they are integrated within the framework itself. And also we give examples of what are the cross-cutting themes, that one can actually have in each of these areas. So I'll give you some examples. So one of the things that I wanted to say that is common across all of these frameworks is that, it is really important to think about the fact that students need to have self-confidence and feel like they belong and have an identity as people who can actually excel in this quantum. So because of that, we actually emphasize that it's really important to maintain a supportive atmosphere that encourages questions and explorations. And it's also very important to offer collaborative exploratory activities. Also, low stakes educational setting is really important when you're really trying to have students do quantum. And when relevant to a STEM subject, it's really important to use a learning cycle approach, so that you think about development of models of quantum system and phenomena, plan and carry out investigations to test those models, analyze and interpret data, obtain and evaluate and communicate these findings, and it's a cyclic process. So let me just show you, and all of these things are there on our Q12 website. So I'm showing you an example here of a standard for high school physics that involves quantum entanglement. And you can see that we have a description of quantum entanglement. It's an inseparable relation between multiple quantum bits, and it's a key property of quantum system for obtaining quantum advantage in quantum information science applications. So in fact, entanglement is going to play a central role in giving us the quantum advantage. Why quantum computers, quantum internet, etc., and quantum sensors of next generation are going to be better than classical. And notice that then we always have an expectation. That means, what will students be able to do? So here it says students will be able to explain that qubits can be entangled with each other and exhibit correlations that are distinct from the classical correlations. And then we also have learning outcomes for each of these things. So here, students will describe interactions through which multiple quantum objects can get entangled with each other. And then we have examples of what kinds of things teachers could do. And notice that these examples could help in developing curricula and pedagogy. So for example, for entanglement, we say, for example, for high school physics, 2 photons can become entangled with each other by passing through some optical elements. Or for example, 2 qubits can be entangled by using a certain kind of quantum gate. You heard about quantum gate. And notice that we also talk about where these things actually connect with the standards that you already have for the next generation science standards. So here, again, I'm giving you another example. This one involves quantum computing, again, the high school thing. And again, we have a description about quantum computers, what is quantum computer key concept? And then what are the expectations here? So students will be able to explain which properties of quantum mechanics allow for computational advantage and the potential applications and challenges in quantum computing. And then again, learning outcome. Students will describe the potential use cases of quantum computers and the advantages they can provide over classical computers, for example, or classical algorithms. And again, we have several examples here, as you can see, and we already discussed that fact, encryption, the fact that our credit card transaction right now is safe because of the fact that factoring products of large prime number takes exponential time on the computer. Remember, you just heard that, if you had a 1300 digit number, it'll take more than the age of the universe to factor that number. And that's basically used to make your credit card transaction safe. But if quantum computers will make it polynomial time, which will make it easy to break that encryption, then we need to think about other post-encryption schemes, and we have thought about it, but those are examples that students will think about. For example, they will also think about other examples of quantum computer, like for example, in drug design and other things. And of course, there are also some examples of how you can combine quantum and classical together to do lots of interesting calculations, because it's not that quantum computers will completely replace classical computer. They will basically supplement them for problems that give us quantum advantage. And we don't have right now scalable quantum computers that you already heard about, but we are making good progress. And in several decades, we will be there, but already quantum industries are robust. And students need to actually think about careers because they're not even finding enough people. And again, you can see that we have aligned it already with a lot of different standards, from NGSS. And so, this can be very helpful in designing curriculum. Again, a curriculum, quantum communication, the same kind of thing. And you can see here that for quantum communication, for example, we have the description, how quantum communication uses entanglement or a transmission channel to transfer quantum information to different location. And what is and again, there'll be expectations about what students will be able to do and what will be learning outcomes. But this is also, again, we provide examples and connections to standards. And you can see that it's very fascinating because, the way that quantum information is very different from classical information. It cannot be copied. If you measure it, you destroy it. So you really need to be careful about how you teleport that information, for example, so students can learn about those kinds of things and, at the level that they are at. And again, we make a lot of connections with the standards, as you can see. So for example, a high school physics standard says, evaluate questions about the advantages of using digital transmission and storage of information, or evaluate the claims, evidence, and reasoning behind the ideas that the electromagnetic radiation can be described either by a wave model or a particle model, and that in some situation, one model is more useful, and in the other case, another. But you can see and communicate technical information and how some technological devices use the principles of wave behavior and wave interaction with matter to transmit and capture information and energy. Notice that these are standards that connect with all these framework components. So this will be really easy for helping develop curricula. Now, I also wanted to show you the cross-cutting themes and how we have made connections, because cross-cutting themes, like for example, patterns, you can see across different topics, or cause and effects. Like for example, one pattern is there are similar, patterns are similar among both classical and quantum computers, and so that means that, for example, encoding information in a physical system, both classical and quantum computers encode information in physical systems. There are different kinds of encoding, but they do it in physical system. Information is physical. Initialize the physical system and transform the information, measure the information as an output. These are all common across classical and quantum computers. And so teachers can actually have those kinds of connections. So here, for example, when you have classical computer, you have classical memory, quantum computer will have quantum memory, classical computer has classical CPU, quantum computer will have quantum CPU, and quantum input and output as opposed to classical input and output. And as we said, decoherence is a huge problem in a quantum system because quantum states are very fragile. And so you can see that we have a lot more on what are the cross-cutting themes and how you can make connections. I think I'm running out of time, so I'll just say that for middle school science, for example, we might have, again, the same topic, right? Because the key concepts are the same, but we will actually have different description, different learning outcome, different possible activities, different NGSS things that might align for the middle school one, because, the teachers at the middle school actually said, these are the kinds of things that will connect with their students. So you'll see that for the middle school, okay, and again, entanglement could also connect with the middle school mathematics, not just, science. And so again, how will that connect? These things describe it separately so that if you are trying to develop it for the middle school class, some curriculum, you would take advantage of this particular thing if you're interested in entanglement. Similarly, if you're interested in quantum computing in middle school science, this framework, this part of the framework will describe how you can actually take advantage of this and what are the things in the standards that connects to it. So this is also, key concepts and what is the NGSS connection for the middle school group, for example. And I'm just showing you here an example that we have come up with of something that we are trying to use right now in developing curriculum where we are taking advantage of the framework for QIS quantum education. And this device that we are using is called block cubes, which is basically a simplified version of what you call block sphere. And you can go to this website. Actually, we just had a physics teacher article about this thing. And this is basically, you can talk about, help students learn about quantum states. You can help them learn about, quantum measurement using games that students can play with dice. And again, these kinds of questions that we have here are inspired by what the curriculum actually does. Or even things like what is the meaning of, quantum state evolving? That's just a rotation of this cube. And again, it could be very exciting, but I would like to stop here by saying that, these frameworks could be very helpful for developing curricula and pedagogies. And, they are basically deliberately not focusing on grand unification across disciplines or across grade levels. So I'll take any question. Thank you so much.
Thank you so much, Chandralekha.